thanks for staying or coming, everyone. We'll just continue pretty much right where Natalie left off. I do want to spend 2 minutes explaining this vulnerability. It's again like a cycle issue during NS unarchiving, again in the shared key dictionary. So basically what you have to know is there's a shared key dictionary that at the top right, you can see it. It's basically an array of values and a pointer to a shared key set. And a shared key set itself is a linked list, so they can have sub key sets. And then they have the number of keys they store, then a rank table, and then the array of keys, right? And so the way the lookup works is you take you want to look up K1 maybe, or let's go with K3. So you want to look up K3, you go to the first shared key set, you hash the value K3 basically, and use that as index into the rank table. And then the rank table gives you an index into the keys array, right? But that index is bounce checked against num key. Okay? And so in this case, it wouldn't find the key K3 in the first key set, it would go to the second key set, do the same thing, find the key K3, and then that's the index for the values array in the shared key dictionary. Why is this important? Well, really the only important thing here is this one invariant that num key must be equal to the length of this array. If that's not the case, then there's a big problem because then this rank table stuff can index out of bounds. Let's see how this init with coda looks like for this kind of object. It's fairly straightforward. Really what it does is like take all the values out of the archive, right? This is like this decode. So it decodes the num key field and the rank table field. Then it decodes the sub key set. And then the first if statement, that's where it makes sure this invariant holds, right? That like key length of the keys array must be equal. And then interestingly, there's a for loop where it tries to look up every key just to make sure that it's like useful, that it can actually look up all the keys. Looks pretty much okay, but let's see what happens when we try to mess with it. So we start with an empty shared key set at the top. We start decoding these values. Okay, num key, let's put in some interesting values, FFFF, and for one. And then we go and decode a second one here. And we do the whole thing again, right? We start from the top, we fill in all these values, and now we actually make a cycle, and this is like not how you're supposed to do it. And you make a cycle back to shared key set 1, and this actually works. There's logic in the keyed unarchiver to make this possible. Okay, and then we decode the keys, and this is okay, right? Like num key and the keys length is the same. And now we try to look up every key. And so in this case, we are here. We decode, we look up the key in shared key set 2, and it isn't being found because the index is 42. That's not the right one. So we recursed to shared key set 1, and now all of a sudden, here we have a memory corruption because now this invariant doesn't hold, right? It's num key is hex FFFFF. So it thinks this keys array is gigantic, but really it's null pointer, and so we can access an arbitrary address and have that be used as an Objective-C object. So that's the bug. It gives us an arbitrary address dereference, and that's what we're going to exploit now. Right, so this is just a summary, again, our bug primitive. So how do you exploit this kind of bug? Basically what you need to do is to create some kind of fake object, and have that object be used, right? So this pointer that's being read, this absolute pointer that's being treated as a pointer to an Objective-C object, and it will call methods on it, so that should be exploitable if we can fake these. In particular, I think it will call like dialog or is NS string on this thing, and so what you would have to do is like fake an Objective-C object, have a class pointer that points to a fake Objective-C class, and then that Objective-C class has the function pointers, and those will be called. So once you have control over that, you can get code execution. Now, the obvious problem we have here is ASLR. So we don't actually know where anything is in memory. We don't know where our fake objects end up when we put them in memory. And we also don't know where libraries are. So we don't have code pointers. And we'll tackle this problem in 2 parts. Part 1 is we'll do heap spraying, which is an old technique, but it still works. And so what you do basically is you allocate maybe 256 megabytes of memory. This is fairly easy over iMessage actually due to the unarchiver. And once we have allocated that much memory, then at this one address, the hex 1170s, there will be control data, our data. And so this is how we can put fake objects into memory. We just spray 256 megabytes, and then our fake objects are located at a known address. And this is pretty good. The second part is more complicated. So the problem we now still have is we don't know any code pointers. And so because we can't inject executable code into the process, we have to know the addresses of existing executable code. So we need library addresses. And this problem, I had two different approaches for that, for tackling that problem. And I kind of followed both, but then I didn't really get the first one to work, but the second one worked. But I still want to go through both of them because I think they're kind of interesting. The idea for the first one is basically to work around ASLR and like deal with not knowing these addresses. So one typical example here is partial pointer overrides. Right? If you like have a 1 byte override into a pointer, then you can do some interesting stuff without actually knowing where the pointer points to. This doesn't work here because of the bug. The bug is like an absolute address deref, but maybe we can do something similar. Well, and the second idea is to properly, I guess, break ASLR and get addresses to then, fake objects and so on. Start with the first one. So the rough idea I had was to do a heap spray without knowing library addresses, but instead having the application itself put in some pointers into the sprayed, into the contents of the heap spray. So maybe it makes it more clear with this image. So my heap spray is at this hex 1170 address, and what I want to put there are fake objects that have some valid pointers in them that the application itself puts in there. And then I have a pointer maybe to some interesting global object. And since that's part of a faked object, maybe I can make the process do something interesting to it. Like that's the really vague idea that I had. One example how this can work in our scenario here is the NSKeyed unarchiver. It allows decoding C-style arrays, like, well, just fixed size arrays. You tell it, like, give me 10, an array of 10, or decode me 10 integers or so. And actually, it also supports decoding class pointers for, I don't know why. This seems like a really absurd feature. But what this lets you do is it lets you create a linear array in memory with pointers to classes. And then if you look at Objective-C objects, and in memory, an Objective-C object is just a pointer to a class, and then the fields that it has, right? And so with that, we can suddenly create somewhat valid-looking Objective-C objects without knowing addresses. So to make this more clear, the picture at the bottom, the archive we put in pretty much just has the string NSArray in it, where it's like, this is an array of classes, and each entry is the class NSArray. So I just need the name of the class. And then the keyed unarchiver will go ahead and like look up the name of this class, look up the class object, and put in the pointer to that class into this memory buffer. And so I end up with this memory dump on the right side. And now this suddenly looks like a legitimate NSArray because the first quad word is a pointer to a class, the NSArray class. And so now I've been able to fake objects without actually knowing any addresses. I pursued this a bit further. I guess the furthest I got was I was able to basically freeze some object and then make the application lower or decrement some ref count. Now that ref count would also be a pointer to a class, or would, like the thing that would be where the ref count would be decremented was also pointed to a class. And so it just so happened that if you look at a class object, the first quad word is again a pointer to a class, a meta class, and the second quad word is the pointer to the superclass, right? So Objective-C has inheritance, and these class objects, the second quad word is always the pointer to the superclass. And now due to this reference count decrement, I was able to decrement the second pointer to the superclass, which is kind of hilarious because it lets you change the inheritance hierarchy at runtime because this is writable, but it's not immediately useful. At least I couldn't really see something immediately to do with this. So I kind of gave up on that idea, but I still think it could be done. There's probably more you can do, like more primitives you can gain by faking object in a similar way or doing other clever things. So that's why I wanted to include it here. The other option that ended up working is, well, properly defeating ASLR, which has two steps or two parts to it. The first part is we need some kind of communication channel to leak data back. And the second part is we have to exploit the bug in such a way that we get some info over this communication channel. So let's deal with the channel first. Here's a screenshot of iMessage. And here you can nicely see the three different states the message can be in. So the first one is read, the second is delivered, and the third is none of those. And the way this works is through receipts, iMessage receipts. And so there's read receipts, which say, yes, I got this message and the user actually read it. And the second type is delivery receipts. And those are sent automatically, which makes it very interesting, by this IM agent process that Natalie mentioned. And so we get them automatically once the message arrives in IM agent. And so this is going to be our communication channel because now we get some kind of information back from the process. So let's build something cool with that, an oracle. On the left, there's some rough pseudocode about how this message processing and IM agent works and the delivery receipt sending. And so the key point here is that the NS unarchiving happens before the delivery receipt is being sent. And what this gives us now is basically a crash oracle, because if we can trigger a crash during the unarchiving, then we won't see a delivery receipt. And if we don't crash, then we see a delivery receipt. So all of a sudden we have basically one bit information leak. Did it crash? Did it not crash? And now the remaining challenge is to crash when some condition is met so that we infer some kind of, some piece of information from that. Okay, so that's the communication channel. Let's go to exploitation. Before we do that, some iOS internals, there's this thing called DYLD shared cache. The idea is you take all the majority of system libraries and you pre-link them into one gigantic binary blob, which is around 1 GB in size, so it's pretty gigantic, and that is shared and mapped in all user space processes on iOS. And there's three things about this that are very interesting. The first is it's always mapped in this address region of 4 GB between 18 and 2870s. The second is the randomization granularity is 4,000 hex 4,000 bytes because of large pages in iOS. But the third is the most interesting one. The shared cache is actually mapped at the same address in every process on the same device. So it's only randomized per boot is what this means. Which means that, for example, if we crash IM agent, we know that when it respawns the next time, the shared cache is still at the same address. Okay, so let's build an oracle. The bug that I showed that gives us the arbitrary address deref primitive basically gives us this oracle function. So we put in some address, and it will only not crash if the address is mapped, and then if the value that's at that address is either 0 or if it looks like a valid Objective-C pointer, which means it can have the most significant bit set, then it looks like a tag pointer, or it actually points to a valid Objective-C thing. So only if these conditions are met will it not crash when we give it an address. Otherwise it will crash. And now we can observe this crash because we either get a delivery receipt or we don't. So that's the idea. So what do we do with this? Part 0, offline, so that this doesn't need network connection. We will basically compile a profile of a shared cache given this Oracle function. So this is really simple. You take the DYLD shared cache, you get it from IPSW, whatever. So you have this huge binary, you take the Oracle function and you just run it over the entire shared cache, and the result is basically like a bitmap, right? Bit 1, bit 0, bit 1, depending on whether this function returns true or false. And so here at the bottom you can see an example profile, and maybe the white area means this is where it wouldn't crash, and the black area means this is where it would crash when probing. In practice there's a third state, because, for example, there's a writable area in the shared cache, and you don't know if that at runtime what will be there. But it's easier to explain with a two-state. Sorry, with a two-state profile. So the next step is then to do some linear memory scan. We know the possible region where the shared cache is mapped. You can see it on the right in this image. And so we just go in, like, for example, 256 megabyte increments and just go over this range, query this Oracle, and at some point it will return true, or like we will get a delivery received, and then we know, okay, we have found some address somewhere in the shared cache, like maybe this 19007400. Okay. The next thing we do is, again, offline. We have to now compute all the possible base addresses sorry, that would lead to us not crashing on this particular address that we just probed. And this is, again, very easy. We just go in page size steps over our shared cache profile. And now in this picture, every white region is now a potential candidate. Right, because this is the 8 bytes that we could have just probed in this case. And so in practice, I think this will leave us with maybe 30 to 40,000 candidates, because the shared cache is gigantic. It's like, like 1 gigabyte or so in size. Okay, so we have all these candidates. Last step, we need to eliminate them until we have just one remaining. And I think this is best to explain with an image. So suppose I just have five candidates left here, and they are now all mapped at different addresses. That's why they're like shifted, right? And you can see the initial address that we probed. It like goes only through white space because it didn't crash, right? So that's the initial address. And now we pick another address to probe, so that roughly half of the candidates will have a 1 bit and the other half has a 0 bit. And so this way, regardless of what this Oracle returns, we are able to roughly discard half the remaining candidates, right? So in this case, if it crashes, then we know we either have the first or the last profile, right? Because this is where the black area is. And if it doesn't crash, we have one of the 3 middle ones. And so we just keep doing this, and in every step we basically halve the number of remaining candidates. And so this is really fast in practice. This takes like 20 or so queries to go from 30,000 candidates to just 1. Okay, so, and this will then tell us the base address of the shared cache. Right, so I think I have just about enough time. So this is what it looks like. We have all the addresses. And this is good enough for any device that doesn't support pointer authentication, which is every device before the iPhone XS. On the XS and newer, Apple has a new feature called pointer authentication. The half-minute idea is that you take everything that's a function pointer, or it can be any pointer in theory, and you sign it at process startup, for example. And so you do this with a specific instruction, as you can see in the bottom. And then you have a signature, and you store that in the top bits. And then before using a pointer, for example, for jumping to it, you authenticate and make sure the signature is actually valid. And if it's not, then you crash. And so this prevents us from doing, like, directly gaining control over the PC program counter. Because we are not able to fake these these signatures. So we need to bypass PEG. So this is pretty much what I said, right? We cannot fake these code pointers anymore. The idea for the bypass roughly is that while we cannot fake classes, we can reuse existing classes. And so here in this case, I have a fake Objective-C object, but it points to a real existing class with signed function pointers. And this will ultimately give me some form of arbitrary Objective-C method call primitive, where we can call any method or almost any method with pretty much controlled arguments. And this is powerful enough. This is all that's necessary. Okay. So we can now execute arbitrary Objective-C methods also outside of the sandbox, because this was on iOS 12.4 where the unarchiving still happened outside of a sandbox, can access user data, etc. We don't care about that, we just want a calculator. The way to do it is you call this one way to do it is you call this one Objective-C method to launch an application named the calculator. And let's see if we can get that to work. Okay. So, yeah, okay. So this is the iPhone I'm using. It's still on 12.4, right? So this is the last vulnerable version, like at this point more than half a year old. And let's start this. I hope it works. Okay, so what you can see now, okay, it's recording. It's kind of unnecessary. Anyway, what you can see now is it's going to do this linear scanning phase, right? And it's nicely telling us what it's doing at this point. And so it's probing these addresses, and I think this step is either 128 or 256 megabytes increments. And so it's testing these addresses, and it's not getting a delivery receipt back, so it assumes, okay, it crashed. And now for this one address, the hex 1b, it did get a receipt back, and now it knows, okay, it has found a valid address. And it did this candidate computation thing, and figured it had 32,000 candidates, and now it's going to roughly half that number with every additional message. So you can see it already went down to 15 or 16,000 roughly, and it will keep doing that. And I think I can actually take questions now while this runs. This will take like another 1 or 2 minutes. So maybe it's a good time to take questions if there are any at this point.
Are there?
No.
Come on, make me run through the room.
There's one.
Hi there. Thank you for your talk, first of all. I guess that only works because iMessage is like restarting in the background all the time, because it's crashing.
Exactly, right. So this is really important. So the IM agent is just restarted every time it crashes. There is one thing that happens is if it crashes too quickly, there will be a respawn delay. Like there will be a penalty and it won't be restarted for a couple of minutes. And so I always have to wait about 10 seconds between 2 consecutive crashes. And this is why I can only probe the oracle once every 10 seconds roughly. But it's still it's really not a big issue. And this is probably something that should be fixed if it's not already fixed. That this daemon just restarts all the time. Yeah. Okay, almost through, I think. Yeah, I'm also almost out of time. Let's see if this finishes in 30 seconds. I don't think it will. But yeah, so it has found the base address now. It's 19A2B 4 zeros. And now it's doing a heap spray. And this is also really, really hacky right now. I think, so I'm like doing this in, as you can say, tell in 24 steps. I'm very certain with some better engineering, you could do the whole heap spray in one single message and like do one single message that does heap spray plus trigger the bug, but I'm doing this in like 25 or so. Yeah, sorry, Steffen. I hope it's gonna work. It better. Okay. Okay, so let's see. So when it triggers, actually the phone freezes, the UI freezes for a couple of seconds. I don't know why, but I think that's what happened now because the second on the clock, the seconds don't move further. Yes. Yes. Awesome.
Just quick question,
that's-
please.
Yes.
Is there a chance that it fails? And if so, do you know why? Is it possible that it fails?
So it's possible that it fails, but nothing that can be that can't be fixed. So one reason is if the this ASLR bypass, if it finds a like writable page and finds something where an actual pointer is, then right now this implementation handles this incorrectly, and also the heap spray is. It would be much better if it happened in one message, because now if like some allocation happens between two of these, then it could fail. Yeah.